the other battery in there too, so it should be good. Okay, have you figured out what it is I want to hear you say? Vora.
I think it's that any edge between two vertices would be conserved.
Yes, preserved. Yes, yes. This edge from x1 to x2 is here, so therefore this edge is here. See, if that edge wasn't there, you couldn't do this, right? Okay, and this is, we get this where the edge theta of xi goes to theta of xi plus 1 exists since xi goes to xi plus 1 and isomorphism preserves edges. You have to say that. That's important to get that down. Okay. Isomorphism preserves edges. Otherwise, you're just making up stuff. You're saying, oh, I have this path in the first graph, I'll just do what I want in the second graph. It's because the edges are preserved. Remember, what is the definition of a graph isomorphism? It's a bijection between vertex sets that preserves edges. And preserves non-edges, by the way. But it preserves edges specifically. So, let me just say, we get this thing here. I'm going to circle it and put a little star on it. And I'm going to say, thus, star is a Hamilton cycle. Get your camera ready? In G2. I'll get out of your way. You have to. Okay, does that make sense? Do you want to do another one of those, or do you kind of get the idea of how those work? I've got one more on the review sheet. I can do it. Basically, I have two more questions to do. One of them is a whole several parts about a particular graph I'm going to draw, and the other one is another one of these to practice on.
What is the one on the
I'm going to change Hamilton cycle to connected. So if you have a connected graph and you have an isomorphism, prove that the second graph is connected.
same process?
It's kind of the same process, but you have to use the definition of connected. Maybe I'll let you guys try that. Does that sound okay? You guys, okay, I'll make a deal with you. You can change Hamilton cycle to any other word you want and practice it and write it out, and I will look at what you wrote and see if I think there's anything missing.
What if we want to change it to prove that if G1 has an edge between two vertices, prove G2 has an edge between those, or the transfer, or the...
You can do that.
Yeah. That seems a bit more cruel, though. I don't
Well,
know.
that's trivial, right?
Yeah.
What are you saying?
Just the
If,
definition of it.
yeah, you're saying if there exists this edge, then there exists that edge?
Mm-hmm.
Yeah, that's just the definition of an isomorphism. No, think of the bigger words. Think of Eulerian trails, bipartite graph, connected graph, cycle of length 4. Okay, or pick your favorite number. If this graph has a cycle of length 4, then this graph has a cycle of length 4. Do I need to be writing these down? I mean, there's a whole bunch of words. I don't think I need to write them down. Just anything that you could describe a graph with. It's got cycles, it's got trails, it's got bipartite, connected, just any of those words. Okay? So this is a sort of question, you know, that I would be more likely to put on a test, but I wouldn't have put it on a quiz because you don't have as much time. But you have to actually write out a proof. Although this is very applied, there's a lot of graph theory, a lot of recurrence relations, something. I guarantee you, you will definitely have to prove something on the test. This is going to not be a seriously theoretical, proofy test, but you will have to prove something, and this would be a good candidate of the sort of thing I might ask you to do. Okay, let me go to one last problem, and this is just to review some of the concepts. Unfortunately, I have to draw a fairly big graph to sort of get this to be interesting enough for us to do. So are you ready to do that? This is the last thing.
Number 9.
Oh, yeah, it's number 8 on the review sheet. I reversed the order because Adriana brought up that graphing isomorphism question. So. By the way, I didn't review today, kind of looking at graphs and constructing isomorphisms between them. We've done a lot of that, and it's in the group works and stuff in the homework, so I probably won't do that today. But I am going to give you this graph. It's going to have a lot of vertices. We have a row of 5. Then we have another row of 5. And then we have another row of 5. So make 3 rows of 5 on top of each other. And then connect them vertically. So you're basically making, this is often called a mesh graph. It's a mesh graph, essentially. And then I'm going to add 4 more edges to this picture. Okay? One of them is from the middle top to the middle right. The other one is from the left middle to the bottom middle. So these 2 little diagonal lines. And then I'm going to connect across here and across here. Okay, that's the whole graph. Let me label the vertices. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. So there is the whole graph, and I have about 6 parts or so of things to answer about this. Lots of practice with the same graph. Okay? So here's the first part. Is there a closed Eulerian trail? And if so, produce one. So does G have a closed Eulerian trail? What are you going to do to answer that question? Find the degrees of the vertices, right? So let's just do it real quick. You guys tell me. I'm going to go across. We'll write down all the numbers because we may as well get this information now. So Anthony, can you do the first row? 2, 4, 4, 4, 2. Okay? Are we good with that? Let's see. Rocky, can you do the second row? All 4. They're all 4? 4, 4, 4, 4, and 4. Yep. Okay. And Adriana, how about the bottom row?
2, 4, 4, 4, and 2.
Okay. Based on that, does this graph have a closed Eulerian trail?
Yes.
Yep. All the vertices have even degree. So now you have to give me one. You have to give me one. So how do you suggest we actually produce a closed Eulerian trail? Alex, do you want to help me with this?
Just start somewhere.
Where do you want to start? You have to start somewhere.
B.
You're going to start at B. Okay, we'll start at B. Oops, I have a marker. Good here. Okay, starting from B, where do you want me to go?
C.
We'll go from B to C. All right. Let's just go around the room here. Peter, where do you want to go from C?
D.
D. All right. Joseph, from B, where do you want to go?
B.
Right back to B again. All right. Now where do you want to go from there, Jeff? I'm at vertex B, and you can't use the blue edges.
A.
A. All right, very good. See? So easy. You can walk right in and solve problems in the middle. Let's see, where am I at? Lisa.
F.
Say again? F is my only choice. So I go down to F. Okay, very good. Christy, you're here on behalf of David.
Yeah.
So David.
G.
G. Okay, perfect. We'll go to G. All right. Adriana, from G, where do you want to go?
L.
L. See, this isn't that hard. You just have to go through the process. Let's see. Anthony, where do you want to go from L? K. Over to K. All right. We go to K. Bora, from K, where do you want to go? Only place you can. And let's see, Nicole from vertex F, where would you like to go next? We're going to take the diagonal over to M. Good. All right, Jason from vertex M, where can I go from there? Over to N. All right, over to N. And Rocky from vertex N, where do you want me to go next?
L.
Back to L again. Okay, so we're back at L. This is why you should bring in like a nice colorful pen or something with you to the test, I think. All right, so let's go back to Alex again from vertex L. Where do you want me to go next?
M.
Back to M again. All right, great. Peter from M, where do you want me to go?
H.
H is my only choice. Jeff from vertex H, where do you want me to go?
I.
You know what? I'm going to overrule you on that. You can go to I, but I'm going to do something a little different just to illustrate a point. So I'm going to go back to G.
No.
It'll be a premature cycle.
And then I want to go to B. So let's just say that happens to you, because see, this is the point I want to make. So you get back to B, and now you're like, I can't go anywhere, but I still have edges that I didn't use. So what do you do to resolve the problem?
Start all over.
Peter would start all over, and he would be the one at the end of the test, like, oh, I ran out of time. So, for those of us who don't want to run out of time, what would we do?
Let's go back to
Create a
zero.
subcycle.
Mark, go ahead. I couldn't hear you.
Insert one, so like maybe start at C, for example, and then.
At C?
Yeah.
Okay, so at vertex C, we could insert something that takes us back to C. So let's just do that. And I'm okay if you do this on your paper. You can draw a big, loop that's outside of the main loop. So from C, okay, Mark, since you suggested, where do you want to go from C?
J.
C to J. Okay, so let's do that. We'll insert J there. All right, I'll just keep going around the room again then. Annalise, from J, where do you want to go? E, all right. Anthony, from E, where do you want to go? D, good. Bora, from D, where do you want to go? I is the only choice, good. And then, who's next over there? Nicole, from vertex I, where do you want to go?
Okay.
Over to J, sounds good. Jason, from J, where do you want to go? O is fine. Rocky, from O, where do you want to go? N. Oh man, it's going to be miserable grading these papers. Can you imagine? Everybody's going to have a different one. All right, from N, where do I want to go?
Make it too big.
I have to go to I, don't I? I have to go to I, and then from I have to go to H, and then from H I have to go to C, right? And I got it. I got it. It works, okay? That was kind of big, but I wanted to give you a big one. I don't want to just say, oh, here's all the small ones, now figure out a big one later. So let's see. Next question, is there a Hamilton cycle in this graph? This will be part B. Hamilton cycle. Is there a Hamilton cycle? So, should I redraw the graph, or is it okay with all the lines on it?
It's a different color.
Well, I don't. Oh, I can borrow one of Joseph's. Okay. Can I borrow one of your markers?
Of course.
Thanks. Let's go with pink. Okay. So, is there a Hamilton cycle? Well, what kind of thought, without figuring out, you don't have to figure out yes or no right away. You can make some notes. And what are the things that you know about such a Hamilton cycle? Can you tell me anything that you would know already about a Hamilton cycle? Remember, you're visiting every vertex exactly once. That's a Hamilton cycle. The Eulerian trail in blue is using every edge exactly once. But a Hamilton cycle uses every vertex exactly once, but not necessarily every edge.
You have to use the two edges that go A, E, O, and K.
Okay, good. A Hamilton cycle must use several of the edges because any vertex of degree 2 has to be visited, so you have to enter and leave along the two edges that are there. So we must use the edge, what is it, AB and AF, right? I'll go highlight these in a second. And then we have to use ED and EJ. And therefore we have to use KF and KL. I'm doing the four corners of the graph basically. And the lower right corner, we have to use JO and NO. All of those have to be used. So let me just highlight those on the picture then. Using the pink here. Okay. Based on those four things, can you see it at all?
Yeah.
There's so many lines on that slow hard. All right, so from there, can you tell me anything else? Jeff?
At vertex J, we've already used two edges, so we can't use it going to I or C and same.
Right, we can now cross off some of the other edges that we can't use, right? So I can't use, so thus, we cannot use, you remember these kind of arguments, right? We did these before? So we cannot use, what was it, the CJ and IJ. I'm going to actually erase them from the picture. Obviously, when I do the next part of the question, I'm going to have to redraw the graph. But for now, I'm going to kind of cross them off. You can even bring your white out if you want. Just make sure you copy the whole graph before you cross off the edges. Is there anything else we can cross off?
FG and FM.
FG and FM, right? So FG and FM. Okay, so we can't use those. All right. Anything else we can say?
Now you have a nice symmetric graph.
Very symmetric. Yeah, that's for sure. On left of is quite symmetrical. So by symmetry, what could you? Is there an edge that you could force yourself to use by symmetry? You look at vertex G, right? There are three. You got to visit that vertex. So you have to use two out of those three edges. One of them is either going to be this one or this one for sure. You might use them both. Actually, you can't use both. So actually, so you have to use this one because if you use both of the other two, you make a closed cycle, right? So let's just write that down. We must use GH. By the way, we may not be going to a contradiction here. We might actually be coming up with a cycle that works. So don't assume it's no. Let's just see. We must use GH. Otherwise, premature cycle, and the premature cycle would have been, I'll just write it down, A, B, G, L, K, F, A. Right? So you have to use GH. And then I'm going to take Joseph's suggestion and use the symmetry. By symmetry, without loss of generality, let's say we use BG. That might be just enough to force enough things to happen. So I'm going to use BG, which means what now?
No G.
Right, so we cannot use GL. By the way, if there's no symmetry, just a second, Jeff. If there's no symmetry in the graph, You can still do this, you just have to treat it as a case. Like case 1, I'm going to assume that we use BG, and in case 2, I will assume we use GL. So if the symmetry is not there, it doesn't mean you can't go down this kind of logic. Go ahead, Jeff.
So can we just, or I'm just wondering, before we do that step, should we also just say we have to use HI for the same logic as GH?
Yeah, we could do that too. Yeah, that's a good point. You want me to do that now?
I was wondering if since it's the same logic as GH, we just make that one step.
Yeah, so I say similar, oh yeah, you don't have to write it all out again. So similarly, we must use HI. Can I just insert that there, everybody? I'm good with that? Does everybody understand what we're saying? If we don't use HI, we're going to get this premature thing here. So I'm going to force myself to use HI. Okay, and I've taken off GL. Anything else I can take off? Okay, I can take off, good, CH and HM, I better write these down. So CH, HM, what else did we say? B, oh yeah, BC is gone. Look at vertex B. BC is gone, and what else is gone? BD, right? Gone. So we can't use any of those. We must be just about done. BC, BD, all these are gone. So, oh, we're done. Because look at vertex C. Right? You don't even have 2 edges left to visit vertex C on. So now we know this graph does not have a Hamilton cycle. Okay. There are a lot of ways to get to the answer. Again, there's not going to be just one unique way to get the contradiction here. So now we don't have 2 usable edges incident with C, and that implies contradiction. So the answer is no Hamilton cycle. Okay? Is that good? All right, can I put the edges back on there? So I can do part C. I have a couple more parts, we're almost done. But there are a couple more things, I think you'll want to see this. Put this edge back here, this edge back here. I think I got them all put back in. There's my graph again. Okay. Part C, you ready? This is quick. Is this graph bipartite? Everybody have the answer? No, you don't have the answer?
No, I do, but it's not about part-time.
I'm just playing with it. Yeah, the answer is no. Why is the answer no? Anthony, do you know? Why is it not bipartite? Circles and squares thing, meaning?
You start by circling and squaring.
Oh, you mean if we go through and start trying to do circles and squares on it? Yes, but what specifically is going to be the problem? Anybody can answer this. It's okay. Yeah, you got a cycle of length 3. Guys, remember we proved in class, this might be a good proof to review. A graph is bipartite if and only if it does not have any cycles of odd length. So this graph does have a cycle of odd length. So let me just write that down. It has odd length cycle B to C to D to B, for example, right? That would be one. There's not a lot of triangles in the picture. There's not a lot of, actually, this is something, and I have caught people making this mistake before. They look at this triangle, FMK, and they say, oh, that's a 3 cycle. They don't realize it's actually a 4 cycle, because there's the hypotenuse here, but you have this side, you have 2 more sides down here. So be careful when you're saying something is a triangle. In geometry, we know what that means. In combinatorics, graph theory, I got to be a little careful. It's the number of edges around the shape. Okay, so that's an easy one. Okay, I have another, two more parts here, and then we're done. Part D, I'm gonna add one more edge to the picture, as if there's not enough already. I'm going to add edge HE. I'm going to add edge HE right here. That's all I'm going to add. This is a new graph. Is the new graph, first of all, at this point, I think everybody should know that we have an open Eulerian trail, because we just made two vertices of odd degree. And so you could go through the same process we did in part A, but we won't do it now. But here's a more interesting question. Is the new graph planar? So I guess we have to figure out the, what do you want me to do here? Count the number of edges, okay. By the way, how many vertices are there? That's easy, 15 vertices. Number of edges, let's see. All right, I just made this into a 5, and this one went up to 3 right now. So can somebody add 2 plus 4 plus 4 plus 4 plus 3 plus 4 plus 4 plus 5 plus 4 plus 4 plus 2 plus 4 plus 4 plus 4 plus 2 for me?
What?
Would you like me to repeat that question?
Can you repeat the question? Is it 53?
Say again? You got 54.
I got 50.
Oh my gosh.
I was hoping like we'd get everybody with the same answers.
Wait.
All right, I'm gonna do it. This is, I can handle this.
I hope so. It's a scary.
14, 17, 25, 34, 44, 54 is what I got.
That's what I got too.
This is how I add up points on tests. That's why I always get it right. Just like 2 numbers at a time. 54. So how many edges are there in the graph? Except on the quiz when I made it out of 33. All right, so let's see. 3n minus 6 would be what? Because that's what you're thinking about, right? 3n minus 6? Am I out of juice there, Joseph?
Oh, no, I just forgot to move to this board.
Okay, that's okay. Say again? 39, so 3n minus 6 is 39, so can I use that inequality? No. Okay, so how about the 2n minus 4 inequality?
No, don't use it.
Can't use it, right? Because I've got 3 cycle, and you know, we've already talked about that. So we can't use either of those inequalities. If it is planar, what should I be doing for you? Drawing it, right? Always trying to draw the graph. So, don't know if I could redraw this.
It's not planar because the lines BD and CJ will always intersect in the same path. If you try to move them, they will intersect with each other. Except in this one.
I'm not very convinced. You're telling me, oh, if I try real hard to redraw it, that they'll always intersect?
Well, why don't you circle?
Depends
the
on how hard I
intersections?
try.
Circle the intersections first.
But the thing is, those are going to move, right? I mean, I can obviously move vertices around. Like I could pull this E in here to the middle, maybe, so it doesn't cross over there. But I'm going to make more crossings there. This is a little tricky.